peak, and basically analyze the area under the peak using some method, typically some sort of fitting routine, and then to use that in a pseudo single crystal type approach, okay, dividing by the multiplicity. The difficulty comes when you get something like this, a peak with, let's say, a little shoulder on and maybe another little peak there. When you get a situation like this, then integrating each of these peaks separately becomes very much more difficult. So this approach can only be used where you don't have a lot of overlap of reflections. And so back in the 1960s, the problem was to extract the intensities for overlapping peaks. So they got over this to some extent because the diffractometers became increasingly high, increased their resolution, higher wavelengths, etc. But it's limited. High symmetry, small unit cells are the only really kinds of structures you can study using that method. And then, back in 1967, Hugo Rietveld overcame this problem with neutron diffraction data. So, and for a long time, this method was more or less used exclusively with neutron data. Now, how does this method work? If you take a digitized powder pattern, it's essentially a one-dimensional XY data set. Okay, so you have your observed points, which you can call Y, at every point I, and so your data set is a sum of 0 to n points. So the ith point is some point on your data. If you take that digitized data, you have normally, so that's your Y value, your X value is normally some increment of 2 theta, let's say, but it doesn't have to be 2 theta, it could be wavelength, it could be d-spacing, depending on the type of experiment. Additional data, you know, sometimes the weighting of or error of the intensity is also stored in a digitized pattern. So what the Rietveld method does is it uses the structural information to produce a calculated YI, so YI calc, and compares it to YI observed. So what is that structural information? So this structural information is based on the things that we know about, structure factors, etc., but also information on the peak shape, information on the background. That's all contained within this function. Because structural information is required, it's a structure refinement technique. Okay? You can't use the method for structure solution, only for refinement. So for structure solution, we use things like the Patterson method or the direct methods that we were talking about, but it's a refinement, rather. This stage is a refinement. And what you are doing is you're minimizing a weighted residual function, where this is basically your weighted residual. You're minimizing this observed minus calculated, multiplied by some weight. So the weight is typically Y obs. Okay, so this is essentially the same kind of R factor that we saw in single crystallography. If you remember, the R1 data was something like sigma F obs minus F calc squared over sigma F obs. Well, that's the same kind of residual. Here the weight is the obs, so you're dividing through by that. So it's exactly the same type of residual. So the function f of x is dependent not only on x but on various structural information. So we can expand our equation to include that information. So here we have scale factor. So remember, when you put your sample on the diffractometer, how much sample you put on, what the voltage and current on your tube are, all of that play an influence on the scale. So you need to refine that value. L is the Lorentz polarization and multiplicity factors combined. So Lorentz was due to the geometry, polarization due to the polarization of the X-ray, and multiplicity because of the collapsing of our three-dimensional pattern into one dimension. Phi is the profile peak shape function. It's over there. There's preferred orientation correction. F is our structure factor. There's background to take into account, and there's an absorption correction factor to take into account. How do we tell how good our fit is? So this is the R profile function, and this is the function that is minimized. There's the weighted profile function, okay, which is a slightly different one. This is the function we normally look at. So the RWP is the one we normally look at to check to see how good our fit is. Some others, there's the Bragg R factor. That's to allow us to compare it to single crystal. So this is essentially the intensity observed of a particular reflection divided by the intensity divided by IOPS. So the difference between them divided by IOPS. That tends to be higher than single crystal values, but it allows you to directly compare. And then there's the structure factor. So this is essentially the structure factor one. So it's the equivalent. It's very similar to that R factor. So we normally try and make a note of all of those. The goodness of fit, or chi-squared. This is the formula for chi-squared as applied in the Rietveld method. And the R expected. So R expected, all of these values you find at the bottom of your output file in something like GSAS. R expected is right at the top because the expected R factor depends on the number of parameters, the number of points. So your number of parameters changes as your refinement gets better. You introduce some more parameters. So the R expected will change. And so it's not normally quoted at the end of your output file. You have to go back at the top of the output file where you did your original output process. Oh, there's some other ones. This is statistical factor. Let's not worry too much about that. Let's talk about heat shapes. So, remember, Rietveld designed his code back in the 60s to handle neutron data. Neutron data is lovely. It's a lovely, simple Gaussian distribution. So, you can just have a simple Gaussian function. There's no problem with it. So it took about 10 years or so before people started using this for X-ray data as well, and they started to use other types of T shapes. So, what have we got here? Oh, okay. Well, before we talk about other heat shapes, let's just tell you a little bit about this. So, this includes the structure factors. Okay, we've got this H function here with the full width at half maximum. Okay, now that's important because the full width at half maximum varies according to the value of 2 theta. So one of the most important things in Rietveld's original code was to say how it varied. And so Rietveld showed, well, if you have a look at any X-ray pattern, you will notice the peaks at the beginning of the pattern, let's say, if this is 2 theta, are very broad, and then as you go on later on in the pattern, they get more narrow. So the peak width at half maximum here decreases as you move along the pattern. But it doesn't decrease in a linear way. And so what Rietveld did was characterize that so that your peak's width varies according to this function. So u times tan squared theta plus v times tan theta plus some w. Okay, so in this way, we can see that we can model the peak shape, and any of you who've been using GSASS will recognize this. GU, GV, GW. G stands for the Gaussian, U, V, and W are the same component. So for X-ray data, all of these are available. Okay, if you look up GSASS, or you'll see that all of these peak shapes are available for you to use. But in fact, most of us use this, a pseudo-void. What is a pseudo-void? Well, here's what we just saw, the Gaussian component just here. And here is a Lorentzian component. So a pseudo-void is just a mixture of Gaussian and Lorentzian functions, and we need some kind of mixing parameter. Here, in GSASS, that's Lx, you'll see. So that's your mixing parameter. What about background? So the raw diffraction profile normally contains significant scattering from the background. In the Rietveld method, as opposed to my research talk, you're interested in the Bragg scattering. But look at the background here. So you need a function to model that background, usually. There are a number of background type functions, a number of ways of doing this. It's manual background subtraction. Okay, you go point to point, and you have linear interpolation between each point. No, that's go back a few years, and that's the only method you could use. I remember when I first started, that was the only method available. And so the background subtraction is quite accurate when you do it like that, but you can account for all these waves and humps quite easily. Typically these days, you use some kind of background fitting. A low-order polynomial is probably the best way of doing it. Okay, but don't use too many. You think you're improving your R factor, but in fact, if you look carefully at your output file, you'll see that they're not actually refining a lot of the parameters. So be a bit careful about the number of background points. So that's the typical way. There are different, you'll see there are various different ones. So simple polynomial, the Chebyshev polynomial, cosine Fourier. In GSASS, this is the default. Okay, and it works for a lot of things, but if you look carefully at your background, if you have a sort of very curved background, this won't do a good job. So better to go for a polynomial. Sometimes you actually need to do a formal background correction. So you use this, for example, when you want to do some kind of total scattering analysis. In these cases, you'll have sample background. You carry out your diffraction on the empty sample container, and you formally subtract it from the data to give you the actual scattering from the sample. It does not take into account any variations due to the sample itself. So you may have a sample that's a little bit rough, and it does not take into account any amorphous contribution to the sample that will give rise to diffuse scattering. So the sort of thing we see here. So here, this is actually from diffuse scattering. And so that wouldn't work for a sample, for a background subtraction. So, Rietveld software, available free, usually. This is the list of all the ones I could think of. There are probably a few more now. Topaz you have on your instrument, I think. Okay. I tend to use GSAS. Full Prof is another one that is very commonly used. That's the version from Grenoble. But these other ones, Jana 2000, that's a very good one that will allow you to do all sorts of strange things like incremental ordering, which you can't do in GSAS very easily. But all of these are available. Some of them are very old. You have to look very hard to find them. I have quite a few of them. Refine and Enprof are very old ones, but they work. They're very good because you can obtain the source code and you can actually look at what people are doing. And if you ever needed to do something for yourself, then those older ones like these are quite useful to have. So, how does it work? Okay. You have a two-stage method. So think of when the Rietveld code originally came out. This was the 1960s. People had to do this kind of analysis. There was no such things as laptops or PCs. You had to do all your computing on a mainframe. You came along with a tape or a set of punch cards where it had a little machine like a typewriter, and you type for each line of your code. So computing time was expensive and computers were slow. So a computer the size of this room was less powerful than your laptop is today. So if you wanted to do something then, you had to write your code economically. And so what Rietveld did was he said, okay, I've got this XY data set. What am I going to do to make it economically, so computer economical? So computationally economical, I mean. So he said, okay, I've got some basic information. I know already, I put into the structure, I know the space group, I know the lattice parameters. I have to give it an approximate peak shape to start with, so I know the peak shape. Roughly. And I also, what else do I know? I will also give a 0 point correction. These are things you start off with. So, if you have all of those things, that enables you to calculate the position of every reflection. So, all of this together gives the position of the reflection. So, you can calculate that you should have a peak here on your XY pattern. So what Rietveld did was he said, okay, I don't actually need all of this background here. That's not contributing to my Bragg intensity. I only need this. And I know my peak shape, so I in fact only need a little bit up to here and a little bit up to there. So what the Rietveld method does is it chops up your profile into the peaks and nothing else. And it says, here's a peak at this point. It's got an influence up to here and an influence up to there in my distribution. So 95%, let's say, distribution. And this is the bit I need to pass on to the next program for analysis. So that first stage, so in GSAS, that's PowerPref. What that does is it just chops up the profile. Here's your peak, sends it to the next refinement stage. So this is quite quick. All you do is you chop it up. You have to run it again every time your lattice parameters change significantly, or your peak shape changes significantly, or for example you put in another phase, then you've got to run it again. But otherwise you can leave it alone and just concentrate on this part. So it's more economical. You don't need to do that part of the analysis every time, and you're only focusing on the area around the peak. And then the second part of the package is the refinement. This is where the least squares analysis. So, looking at the individual stages, the starting model. Rietveld relies on a starting model. So, we saw the ways your starting model could be a known structure, a known analog, a partially known structure. So you might have some of the atoms, but not all of the atoms. An educated guess, a structural distortion, or a structural model from ab initio techniques. This one is the most difficult and most time-consuming. Okay, but the others are common. These ones we do all the time. This one is more difficult. I won't talk very much about that, but just briefly. So your refinement parameters, so the background, 0-point correction, peak shape parameters, and a scale factor. So those are known as the profile parameters. Then you have your structural model, which contains your unit cell dimensions, atomic coordinates, thermal parameters. The absorption coefficient is about the sample. Preferred orientation, again, is about the sample. Fractional occupancies and any phase fractions, again about the sample. And these are the things you need to know before you start your analysis. So your unit cell dimensions, approximately, or reasonably accurately actually. Z is the number of formula units per cell. The space group, so your approximate atomic coordinates, your wavelength, the approximate peak position, and for XRD that will be pseudo-void, will be the normal peak shape that you use. So, and this is the sort of thing that you put in. So this is your these are your atomic positions, X, Y, and Z. Your fractional coordinates, your fractional occupancies, the name, and some thermal parameters. So those are your atomic coordinates as they go into GSAS. Here are your profile coefficients. So U, V, and W of so how the peak shape varies across the profile. LX, the mixing parameter. There are some other ones here that I think you'll need to know about. So trans is a transparency factor. It tells you a little bit about, it shifts some of the peaks, particularly at high D spacing, so you have to be careful. Shift, especially when you're using your high temperature stage, is the parameter that describes the height of the sample. You cannot refine shift at the same time as zero. It's a meaningless thing. Okay? And similarly, transparency, you shouldn't refine at the same time as zero. It's too highly correlated. This is what you get out. So this is sodium magnesium phosphate. This is the crystal structure from a while ago. And it's a reasonable fit. So you have observed points, calculated in green. Here is your difference, and these lines here tell you about the positions of your reflections. And they should align more or less with where your reflections are calculated. This is the final output. And what you get are your fractional coordinates. some thermal parameters, and you can do, it's like any crystal structure, you can use software to draw pretty pictures. Okay, this particular one was a nice one, a star-shaped compound with some phosphate units around this central sodium ion. Okay, how do you start a refinement? What's the strategy that you should use? There's no one way. Okay, that's the first thing I should tell you. I can't give you a set of rules that will always give you the answer. This is trial and error, but generally you'd start in this way. So firstly, you'd start with your scale and background. Okay, you've got to get the scale right and you get the background right. In between each step here, do a plot. See how well your data are fitting. That's your indicator to see if you have got something horribly wrong, like your cell dimensions are completely out, you'll see no peaks in the calculated pattern. And then you have to do other things like go and refine your cell dimensions outside of GSAS or outside of the refinement package to get you a reasonable starting value. Your lattice parameters would be next, along with any 0 point. Peak shape. Your fractional coordinates next. Then your thermal parameters, which are heavily correlated with the fractional occupancies. For X-ray data, you probably are not going to be able to do fractional occupancies very well. You don't have enough data. If you want to refine isotropic thermal parameters, collect more data. That means collect up to, so on a typical scan for Rietveld analysis is 5 to 120 degrees. If you do less than that, so 5 to 90 degrees, which is shorter, you can get your cell dimensions, but you won't be able to do a lot of these things. You won't be able to refine isotropic thermal parameters very easily, at least not very accurate. Anisotropic thermal parameters, on a very, very good day. With very high quality data, you might be able to do that. But not normally for routine powder X-ray diffraction. You just don't have enough data to do it. Remember, an isotropic thermal parameter only has one parameter. Anisotropic has 6. You just don't, your parameter to data ratio changes enormously when you start doing anisotropic parameters. And then preferred orientation, extinction, absorption, depending on what you might have in the sample. Sometimes you have such severe preferred orientation, you have to do this early on to get, much earlier in your refinement, just to get the data refined, the model refined. So the initial refinement is going to be very dependent on reasonably accurate cell dimensions. Your 0 point and peak shape parameters. Okay, so accurate cell dimensions. You'll see straight away if you're far out, and you don't need to be very far out. Your refinement will just never work. You will just be refining a background, and that's it. So what you're going to need, don't just look at R factors, look at the plot. So you may need to refine this independently outside of the model. So, okay, so what is this? This is, right, one of my hobbies is to repair very old cars. Okay, I like to work with my hands, so I've got some very old sports cars and I like to work on them. When you're trying to do work on these cars, it's often useful to have a manual, and there are manuals available, and each of them has a fault finding chart. So your fault finding chart will tell you, the engine is not firing, and it gives you a list of possible reasons, and then how to fix it. This is a fault finding chart for Rietveld analysis. Okay, so for example, The program crashes on initial refinement with background and scale refining. So this is just the initial refinement. What's wrong? Okay, so too many phases in a multi-phase refinement. Okay, sorry, this is here. One, as above, so all of these. Initial scale or background too far out, you're not close enough. Background incorrect, e.g. poor background function or wrong number of background coefficients. And the other ones were bad data, data set corrupted, in wrong format or has gaps. So how to fix it? Reformat or recollect the data. So some more sophisticated one. Refinement crashes on introduction of lattice parameters or 0 point. Poor data, wrong space group, symmetry or crystal system, poor starting model. How to repair it? So poor data is recollect the data. Wrong symmetry, examine data carefully for split or absent peaks, change lattice parameters or the space group accordingly. The poor starting model, use a better starting model, fix lattice and 0 point and refine positional parameters of the heavy atoms to improve the model. Okay, so when you're refining the atomic positions, it's remember which atoms are heavy. So, for example, if we were looking at bismuth oxide before. So a bismuth oxide, you've got bismuth, and you've got oxygen. Well, bismuth is very heavy, 83. Oxygen is only 8 as a scattering, as an atomic number. So its contribution to the scattering is very small. So clearly, in X-ray data, it's very difficult to refine the parameters for oxygen. So I wouldn't even try. So don't try to refine those, just refine the bismuth. Was there anything else? Yeah, these are, I mean, this will be available to you. You can use this to help you to, as a manual, if you like, when things go wrong. Okay, so just to finish off with, just to mention about some of the tricks of the trade. So you start off with when you're starting to introduce your atomic parameters in your refinement, what do you want to do? So start by trying to reduce all of the variables that you've got. So be careful. Space group symmetry is important. Now GSAS automatically tells you when you're allowed to refine a parameter or not. So for example, if you have a non-centrosymmetric structure, so let's take a space group like P21. P21, okay, is a non-centrosymmetric structure. So you can have atomic coordinate, you can have an XYZ coordinate. That's fine. But where is the origin on P21? There isn't one. It's anywhere along the B-axis. So in P21 symmetry, your origin is not defined. It's not defined with respect to the B-axis. So your origin can be anywhere. So be careful. You can't just say refine all the atomic coordinates because the origin is not defined. You can only refine X and Z. Y will just float around. It doesn't know where to stop. So for something like this, for a non-centrosymmetric structure without a defined origin, you have to take something to fix Y. So what we normally do is we say, if it's a structure containing a heavy atom, we put the heavy atom and say Y is 0, for example. It doesn't matter the actual position of Y, but we don't refine it. we fix. So we fix that one. So Y will be fixed, and you allow the other atoms to refine around it. So be careful of those situations. Space group symmetry is very important. If you're not sure of your space group symmetry, you should look up your structure in international tables. Okay, so I'll just show you, right, international tables. Let's see, we've got it here. Have a look at international tables, a page from international tables. I was here 1 second. So volume A, just to show you. Now you should be able to get copies of this in the library. If you have, I mean, this is a standard textbook. Somewhere you should have something like this. I'll just move you to a space group. Right, so this is the data reduction, the unit cell. Right, so here we're at space groups already. These are the two-dimensional ones. I'm just going to get to the right. So down here we're already into the space groups. So if we look at P21, let's find it. Here's P21, unique axis B. So you can see here your coordinates x, y plus a half, and z. Okay, so the origin is undefined, so we need to fix that on something. Okay, so when you're not sure about your space group, it will say, where is it? It says origin at 0, y 0. So y is not actually defined. So if you get a situation like that, check the space group symmetry, and it will tell you if you have this problem. A couple of other things to watch out for in something like GSAS. For certain for certain space groups, there are 2 settings. Okay, so if we take, let's think of one where you would have 2 settings. So some hexagonal groups, for example. Let's do one thing. Let's just move this down here. So maybe it's a hexagonal group. Think of one. Origin, you'll see something like this. Origin choice 1. So here's the space group. Tetragonal I41 over ACD. Origin choice 1. Okay. Now look very carefully. This is a centrosymmetric space group. What you have to be careful of are things like this. It's centrosymmetric, but look, the center of symmetry is not defined so that you get minus x minus y minus z. Okay? GSAS needs that setting. So in this case, you need to use the other setting. So origin choice 2, you need this setting with minus x minus y minus z. Be careful when you're reading a structure from the literature, and it falls into one of these space groups with 2 settings. that you translate the settings, you translate the atomic coordinates into the ones that correspond to this. And there's usually, it tells you, somewhere it tells you the relationship. So if you look back on the previous page, yeah. Origin at bar 1, which is what you're after, okay, at 0, minus a quarter, and 1/8 from bar 4, which is the one in the previous setting. So that's what you have to shift your parameters by, your atomic parameters. So you have to add, or you have to subtract a quarter in the y coordinate and an 1/8 in, add an 1/8 in the z coordinate. So it happens all the time, and people say, oh, the structure doesn't agree, and they come along and I say, no, actually you've used the wrong set of coordinates, you've got to shift. So that's another tip. I think that's it then. I think I've covered my lectures. Thank you all very much for attending all of them. As this is my last day, I wanted to thank you. I brought a few sweets and things if people would like to come and have. It's been a real pleasure coming to see you and talking to you, and I've enjoyed your hospitality here very much, and I hope to come again one day.
Is there any question? If not, thank you very much for your nice lectures and actually everything.
See, I finished on time even though we started at